So what's up again, Benil Game Devs, and welcome to Module 7 of Data Structures and Algorithms. And this will be the last module for this course, and we will be discussing trees. So trees are data structures that are commonly used in the programming and development world, wherein, for example, here, this was gotten from my artificial intelligence class. So we built trees here in order for our agent to find its way from one point to another. So this is from my pathfinding module. So we built trees using waypoints. So as you can see here, we have a couple of waypoints here. So here, our waypoints, when put together, they can build trees. A tree is a hierarchical data structure which is composed of nodes, edges, root, and leaf. And a perfect example of a usage of tree is, for example, your computer drive, right? So you have a root directory, which is your drive. And then in that directory, you may have a couple of subfolders, which also contain a deeper level of subfolders beneath it. And for the parts of the trees, we will look at that here. So trees in theory, let's discuss the parts of the tree. So every item in the tree is a node. So every circle that you see here is a node. So 68 is a node, 95 is a node, 420 is a node. So each node contains a value, as you can see. And the node at the top of the tree is the root. So the root is a very special node inside our tree. So here, as you can see, 68 is our root. So a root is a node that doesn't have a parent node. So one good characteristic of a tree is every non-root node has one and only one parent. So every non-root node cannot have more than one parent. So as you can see here, 12 only has one parent, which is 68. 57 only has one parent, which is 12. So let's look at it here. So 115 only has one parent, which is 16. So that's one good characteristic of trees. Every non-root node has one and only one parent. So always remember that. So 12 cannot be a parent of 42 because it's already a child of 68. So always remember that. That's very important. So every non-root node has one and only one parent. And here, a leaf node has no children. So our leaf nodes here are the lowest level. So 420 doesn't have any children. 95 doesn't have any children. 32, 854, and 115. So these are our leaf nodes. So a singleton tree has only one node, the root node. So if this tree only has 68 in it, so that is called a singleton tree. So we're going to be a little bit more specific in our tree. So here we're going to look at binary trees, but later on we're gonna look at binary search trees. So for a binary tree, every node has either 0, 1, or 2 children. Okay, so that's very important to remember. So as you can see here, number 9, our root node only has 2 children, 4 and 17. 17 has 1 children, and 22 has only 1 children, right? So here, 6 has only 2 children. So you cannot go more than 3 children. As you can see here, let's just go back to our previous slide. 42 has 3 children, right? So this is not a binary tree. So here in binary trees, every node has 0, 1, or 2 children. And since we cannot go more than 2 children, children are referred to as left child or the right child. So for example here, 4 is our left child of our root node, which is number 9. 3 is the left child of this node. So 22 is the right child of 17. So what's important to remember here, I cannot stress this enough, is that for binary trees, every node has 0, 1, or 2 children only. So let's take a look at complete binary trees. So every level except the last level has 2 children. So as you can see here, our root node, which is 15, has 2 children, 22 and 4. And since this is the last level, it doesn't need to have 2 children. Okay? And in the last level, the leaves are at the leftmost position. So for a complete binary tree, for example, this node has only one node. So it must be placed at the leftmost position. Okay, so 3 is the left child of node 4. So let's take a look now at full binary tree. So every node other than the leaves has 2 children. So as you can see here, this is a complete binary tree because all of them has 2 children. So by definition, a full binary tree is a complete binary tree. So let's take a look at the particular tree that we are going to code. So binary search trees. So this binary search trees can perform insertions, deletions, and retrievals in O of log n time. So here, we have a couple of rules. The left child has a smaller value than its parent. The right child always has a larger value than its parent. So the next one is everything to the left of the root is less than the value of the root, and everything to the right of the root is greater than the value of the root. So with these behaviors in mind, binary search, if you remember from our previous module, binary search algorithm works best for this kind of data structure. So let's take a look at a binary search tree here. So as you remember, let's go back. The left child always has a smaller value than its parent. So let's look at the first left child. So 3. So 3 is less than its parent, 15. So the right child always has a larger value than its parent. So let's take a look at 22. So 22 is larger than its parent value, right? So let's dig in deeper. So 18 is less than its parent. So it's in its left position. So it's 22's left child. And here, let's take a look at the right child of 22, which is 25. So 25 is larger than 22. So let's go back. Everything to the left of the root is less than the value of the root. So here, let's take a look at the left half of the root. So 3, 2, they are both smaller than 15. And everything to the right of the root is greater than the value of the root. So everything from the right of the root is greater than the value of this root. So here, this is a perfectly built binary search tree. But you guys might ask me, sir, how are we gonna build this thing? It seems very complicated, very complex, and we all have to deal with nodes and edges and all that. So let's have a little exercise for our insertions. So here, we are going to insert values 25, 20, 15, 27, so on and so forth. So we are going to build this thing. So the first value that we are going to insert will be our root node. So let's put a circle here. So this will be our root node. So 25. Let's just mark it. So for the following elements, we will be putting it at the next empty slot, right? And we will be following the rules that we have talked about earlier when inserting these values. So let's go ahead with 20. So 20 is smaller than 25. So it should be at the left part of our tree. So let's just put this here. This should be 20. Now let's put 15. So where are we going to put 15? So 15 is less than 25. So let's go down to the left. So 15 is still less than 20. So it should go left of 20. So let's put this here. This should be 15. So next is 27. So where should we put 27? So is 27 greater than 25? Yes. So it should be at the right of 25. So let's put another node here. Let's connect it. So 27. So let's take a look at 30. So 30 is greater than 25. That means we're going to the right. So 30 is still greater than 27. So that means that we're going to put it at the right node of 27. So now let's take a look at 29. So 29 is greater than 25. So obviously we're going to the right. 29 is still larger than 27. So we go to the right. So 29 is less than 30. So we're going to put it at the left child of 30. So 26 is larger than 25. So we go to the right. 26 is less than 27. So that means that 26 will be the left child of 27. Let's take a look at 22. So I'll give you guys a minute to figure this out on where we are going to put 22. So let's solve this. So 22 is less than 25. So obviously to the left. 22 is larger than 20. So that means that 22 will be the right child of 20. So let's just put this. Let's move this here. 22. Let's move this a little bit to the right. There you go. So lastly, 32. So 32 is larger than 25. We go to the right. 32 is still larger than 27. Go to the right. 32 is larger than 30, so that means that 32 will be the right child of 30. So there you go, guys. This is how we build a binary search tree. So if you followed all the rules, then it shouldn't be too complicated. So as you can see here with binary search trees, the reason why we can retrieve, delete, and insert data in O of log n time is because we always split the tree in half when we are dealing with its values. So for example, we want to search for 26, right? So since this tree is arranged the way it is, we can do binary search for this one. So we are searching for 26, remember? So 26 is larger than 25. So that means that 26 is on the other half, on the right half of 25. So that means that we have just eliminated all the values from the left of our root node. So we will now traverse here to the child node of 25, so 27. So since 26 is less than 27, that means that we have just eliminated searching to the other half of the 27. So that means that we will go to the left. So since we have found our value, we have just eliminated a couple of steps in order to do that. So always remember that operations inside our binary search tree is O of log n when it is perfectly balanced. So why did I say that? Because the order of insertion of your values can affect how your binary search tree could look like. So for example, let's insert the following values. So let's insert 32. So this will be our root node. Always remember that the first value that we are inserting is our root node. So let's go ahead and insert 25. So 25 is less than 32. So that means that it will be inserted to the left. So 25. So now let's insert 10. So 10 is less than 32, less than 25. So that means that 10 will be the left child of our tree. And then lastly, let's put 6. So negative 6. So 32. So negative 6 is less than 32, less than 25, less than 10. So that means that negative 6 will be the left child of our node 10. So as you can see here, this is a pretty unbalanced binary tree. And here, essentially, if you're going to, for example, look for negative 6, you are doing that in O of n time. So this is basically a linked list. So if you'll see here, these values are sorted from descending order. So if we do it the other way, ascending order, this would be dominant on the right. So that would essentially be a linked list. So operations will still consume O of n time. So you should always take note of the order of values that you're going to insert. Otherwise, you're going to end up with a pretty unbalanced tree. And there are kind of trees that are self-balancing. By that, I mean that they are shifting the nodes on which node should be the node, which should be the left and the right, every after insertion and deletion, just for it to keep the tree balanced. And common examples of those trees are KVL trees and red-black trees. But we're not going to deal with that because I just want you guys to understand how trees work. So that's it for this part. Take a break if you want to. And be ready to fire up your IntelliJ IDEA on the next part. So I'll see you on the next part of this module.